In this lecture, we're going to talk about one of the most important results of probably 20th century science. Many say this, but it's possibly not exaggerating. But we want to talk a little bit about the history leading up to it, and we want to kind of go through the mathematics of it, and with our knowledge of Hilbert space and quantum mechanics now, and show some data as well. So the story goes back to the early days of quantum mechanics when still being formulated, and specifically to the time of 1927. This is the Solvay Conference. The Solvay Conferences were a series of conferences that were critically important in the development of physics. The 1932 one is another huge one. But the 1927 one is important for quantum mechanics because it's 2 years after the theory comes out, where we have Heisenberg hiding back here, who came up with the theory, and Wolfgang Pauli, another important one, and others, trying to find here. And we can see these are some of the biggest names in physics at the time. Of course, we have Einstein sitting right in the middle, Curie here, and so on. And here's Schrödinger. Here's the other one. So Schrödinger and Heisenberg are the two ones who developed different formulations of quantum mechanics, and they are slightly different. They disagree with their approaches, but later on, Dirac, who's hiding here, where is he? He's right in the middle. Dirac here, kind of, and others show that they're equivalent actually later on. But so these three people, actually four, I should say, Heisenberg, Pauli, and Bohr. Where did Bohr go? And I'm over here, right over on the edge here. So these three people are kind of like the trio, instrumental core trio, trying to propose and push forward the theory of quantum mechanics as Heisenberg is developed, but also discuss the foundations of it and explore it. Now, in this earlier and in this conference, there was a very famous series of debates between, especially these three and Einstein. And so there was kind of a schism here a little bit, where really Einstein and Schrödinger are sort of in the same camp, even though there's some divisions between them, but eventually they kind of become unified. And these three, Bohr, Pauli, and Heisenberg. Pauli is a very forceful character, and so is Bohr, but in a different way. But these debates really hinged on what we call the interpretation of quantum mechanics. And there's other stories that happened at this conference. There's been books written about this particular conference, and it's an interesting history. But we'll just show some other pictures here of this era. But during this period, though, there's this kind of ongoing debate, primarily between Einstein and Bohr. Bohr is a very kind of vocal proponent. He's kind of like the father of quantum mechanics. Pauli and Heisenberg are very young at this time. They're in their 20s. Pauli's a little bit, Bohr is a little bit older, and he's kind of guiding them, forcing them in a particular direction and trying to come up with this theory and developing and what its meaning is. So we have these pictures during this, some of the debates between Bohr and Einstein, and they're very famous in the history of quantum mechanics, where basically Einstein would come in, during the conference was kind of the general theme of the story, is that Einstein would come in at breakfast and propose some Gedanken thought experiment that proved that quantum mechanics is not complete or has a hole in it, and there has to be something else going on. Bohr would kind of hum and haw, and eventually he'd come back and answer him. Sometimes the next day he'd come back with an answer to Einstein, often involving the complementary principle or the uncertainty principle behind that. And again, here's the trio of Bohr, Heisenberg, and Pauli. This kind of famous trio, all eminent physicists in the history of physics. And this debate kind of goes on. And I'm not going to go into those debates because that would take a lot of time. But we want to kind of get to a particular argument that happened later. So again, the conference is 1927. These kind of debates go back and forth, and Bohr is pretty much winning these arguments because quantum mechanics is working. But in 1935, Einstein writes, now he's in Princeton, writes a paper with Podolsky and Rosen. Actually, Podolsky did most of the writing, and Einstein wasn't really happy with the flavor or the way it was written. But regardless, it's an extremely important paper in the foundations of quantum mechanics and philosophy of science, if you will. And it's published in the prestigious Physical Review, which is the top journal. Now, when Bohr first read this paper, he said it was kind of a bolt out of the blue. He was kind of shocked that it was kind of like this very concise, well-defined argument showing that quantum mechanics is not complete, meaning that there's a reality underneath that we just don't see. So Bohr took a couple of, I think it was a couple of months, maybe weeks, I think it was months, or a month or so, to write a reply. And his reply was kind of, in the style of Bohr, was kind of opaque and maybe not so clear, but he kind of gives the traditional defense of quantum theory, but essentially saying that quantum mechanics is what it is. It's our best theory of nature. There is nothing beyond it, in the sense that quantum mechanics is inherently random and things do not have a definite state. Now, the 1935 EPR, as it's known, his paper, is essentially, we've been talking about, related to entanglement. Eventually, that's what it comes out to be. But the idea back in 35 was that it was talked about in terms of position and momentum. Now, at the time, though, a lot of people thought, okay, this is all interesting about the foundations, but it's really not, it's not helping in developing quantum mechanics in the 30s and 40s, where people are starting to develop quantum field theory, going further with it, developing it, applying it, and it's working. But this was kind of more of a foundational saying, it's not the final say. But at the time, people thought, well, this is just kind of like metaphysics. It's not, we're never, how are you going to, the idea is, how do you prove that something is not in a definite state without measuring it? So how do you actually determine something before you measure it without doing a measurement? And so a lot of people said this answer would, the answer would never come. There'd be no experiment to be able to figure this out one way or the other. So a lot of people just kind of ignored this discussion. So it took about 30 years for someone, John Bell, another well-known, very famous physicist nowadays, to come up with a set of conditions that must be met for objects to have definite values, meaning that this is a way to discriminate between Einstein and Bohr. And what he comes up with are called Bell inequalities, and he came up with one particular one, and then there was others, and there's just a variance of them. And really, what it is in terms of probability, it's a tool to determine whether there exists a joint probability distribution or not. If you satisfy the Bell inequality, then there can exist a joint probability distribution, and you can describe it with things having definite states. If you violate the Bell inequality, then you cannot have a joint probability distribution, and it's not possible to assign definite values to all possible observables at the same time. That's the way we want to view it here, in a simple way. At the time, what it really was, the terminology used is called local hidden variables. Local hidden variables mean the real states that we don't know about. That's why they're called hidden. And this is what Einstein essentially believed in, though he didn't call them that. So this was a kind of a condition that must be satisfied if there exists local hidden variables. And now we're not going to talk about the version that John Bell came out. It's actually it's not that hard. It's actually pretty simple. But we want to kind of get the ones that really kind of first experimentally showed something interesting. And this is given by, a little bit later, 69, by Clauser-Horn, Shimoni, and Holt, just a CH-SH inequality. So it's another Bell inequality. So nowadays, these term Bell inequality kind of is an encapsulating term for many different types of inequalities, depending upon the system. The original one by John Bell had 6 random variables. This one has 4, but actually the original one is a little simpler because it only has 3 terms in the inequality. This one has 4. And it's easier to, this one is easier to implement experimentally. So let's look at the setup. So we're going to do it schematically, and there's some things we're going to have to go, we might have to introduce with that, hopefully the lecture will back this up. And it goes as follows, and this is a very schematic view of this. So we have some source here, which could be described, we could go into more details about that, and we'll do that in a different lecture, if we haven't already. That spits out an entangled pair of particles, we're going to call, or just a pair of particles for now. And so there's a source, and then we consider pairs going off to Alice over here, indicated by A, and Bob over here, indicated by B. Now each individual has a choice of 2 options of how to measure it. So Alice has 2 choices, one A0 we'll call it, and A1. Now the way we want to think about this is just think about it coming through, say, a polarizing beam splitter, and just changing the angle. So that's why these are kind of set at angles. So we want to So there's two different ways to measure the, and you're setting the polarization bases to measure in that particular basis. So there's two bases that Alice can do a measurement in. And when we look at the outcomes, we either get a plus or minus. There's a two-state observable. Same for Bob. He has two possible settings, B0 and B1. And again, we're going to express those as angles eventually. We could think of it in terms of polarizer. And we'll post some information about explicitly talking about the experimental details. Now, this is a schematic view, but we want to make an even more schematic view just to kind of get our head around it. That we don't necessarily want to be talking about quantum mechanics per se. We just want to think of this as a black box scenario. So there's some box here, which actually would be this part here. Alice inputs her choice, we'll call it 0 or 1, which determines which settings he's going to do. And Bob will input his, which we'll call y, so it gives which setting he's going to have. And they get outputs, which is plus or minus 1. If we could talk about binary, I think we're going to skip that. But they output plus or minus 1. So it's just like, think of it as a box. Now, of course, here we want to think about Alice and Bob being space-like separated to make this more dramatic. Otherwise, you can get around it. So put them on different galaxies, say, for example. All right, now some details here. Each detector now, here, can measure plus or minus 1 variables, as we said. And we're going to constrain this, which turns out to be true experimentally, is that the means are all 0. So if you look at the mean of any one, it's 0, meaning that it's equally likely, just looking at the data of one single setting on one single side, it's the same, it's 50-50 if you get a plus 1 or minus 1. And also, if they do that, and they're plus or minus 1 variables, it turns out that the correlation, which is what we're interested in, the correlation between Alice and Bob's results, turns out to be the second moment, which we did in our exercises on probability earlier on. Sometimes this is denoted by E, AI, BJ. Or again, I and J are going to be 0 or 1, depending on which case we have. So really what we want to look is just at the second moments. And that's actually easier to calculate than the correlation. And we want to see, we want to have some measure, if we will, that can indicate whether a joint probability distribution exists or not. So one way we want to start to build this up, and this is going to be the part we have to think about this. We want to think of elements of reality, really just random variables. And these are A0, A1, B0, and B1. They each have plus or minus 1. And they have in each run of the experiment, we want to think of them as having definite values. And we're making this assumption. So we want them to be elements of reality. So in any run of the measurement, as the particles go out here, the particle has a definite value for A0, it has a definite value for A1, again, those being plus or minus 1, and same for B0 and B1. And what we demand here, if Alice and Bob are in different galaxies, space-like separated, is that the elements A0, A1 are not influenced by B0, B1, or vice versa, because that would violate causality. So this is kind of setting up our story to build this tool. Okay, so let's build the tool. Now what we're going to do is instead of, I'm going to show the function and then consider it. So we're not going to motivate this, but we'll see that it is a tool and it does work, hopefully, convincing. So consider this function. We're calling it little s now. And again, we're thinking of these as elements of reality where these take on values of plus 1 or minus 1. I'm going to write them in this particular way. A0 times B0 plus B1, parentheses. Parentheses don't really matter, but it kind of highlights what we want to get at. And A1 times B0 minus B1. And what we want to do is look at all the possible values. We'll simplify and just look at the B values, Bob's values, and see what it takes if we examine all possible values of B0 and B1 with the assumption that they have definite values in each run of the experiment. So let's take a look here. So again, the parentheses is meaning to be B0 and B1. So if B0 is equal to plus 1 and B1 is equal to plus 1, it's clear that B0 plus B1 is going to be 2, and if you subtract them, you get 0. So what we're saying is that in a particular run of the experiment, these would be the outcomes. There's the determined plus 1 for B0 and B1. This is the result. If the outcome is plus 1 minus 1, we get this result, and so on down the table. There's a mistake here. There's a 0 here. Let's correct this. That's a 0. Forget that one. That's supposed to be a 0. Okay. And so these individually are plus or minus 1 variables. So if we multiply it by a0 and a1, it's not going to really change the story here. We see that whenever we add up these two terms, we're going to get plus 2 or minus 2 in any single run of the experiment. So that puts a constraint on things. But what we want to do is average over many runs. And so when we do that, we want to define capital S to be the average of, say, this one over many runs. And it's going to look as follows now. So when we do this average, remember, think of this as expectation. We want to write it out this way. So we're just taking the average value of these. And now we can factor this out or carry out the parentheses or distribute these through, I guess is the way to say it. And we get 4 terms. We get A0, B0, A0, B1 plus A1, B0 minus this last one, A1, B1. And that's this is the quantity that we're going to be interested in. And these are the expectation value of these two random variables in this experiment. And again, we can calculate this in quantum mechanics, which we'll do later. Or we could do this, think of this classically. It's a second moment. Very easy to calculate with our probabilities if we have it, if we have a joint probability distribution. Okay, now, so what this says now, remember what we said here, is this is if these have definite values. Now, we could go on and I could try to motivate, but if in some way the choice of A0 or A1 somehow affected the outcomes here, then you could get something greater than 2. And you might want to play around with that a little bit. I would recommend doing that. And there's a very simple model you can come up with just to say you can get S up to 4. And that would show that, well, then your choice of A0 or A1 is somehow affecting the outcomes of Bob's particles, which again seems to violate causality, right? Which we'll come back to. So if there's if the AI is no one way influence BI, and vice versa, we can make the argument, we can flip the argument. We have that this value of S has to be bounded by 2 and minus 2, because again we can have minus 2 or 2. Again, you want to think about that carefully. You might need to go through and think about it, but again, you can't get a value of S larger than 2 if A0 is not contextual, if you will, or does not influence, if you will, the B results, and vice versa. This inequality here is called the CHSH inequality, this S, with these terms here. There's actually 8 inequalities given by distributing the minus sign around, because it's just symmetric, and then, say, multiplying by everything by minus 2. Well, that's what this does, these two sides. So, now, if the means are vanishing, like we said, that's our constraint we're going to put in there. We don't have to have that, but if we put in, then it shows that this is a necessary and sufficient condition for the existence of a joint probability distribution. Okay, so this is a bit to swallow, but you think about it, again, go back over it and just convince yourself. And what we want to do is go a little further with this and show some examples, some extreme examples, that will hopefully convince you that this is a good measure of the existence or not of a joint probability distribution. So let's look at this in a little more detail. So here's our inequality up above. And I want to look at 4 particular cases. Well, 3 cases and then generalizing it a little bit. And these are not all the possible cases that we can get, but these are easy ones, if you will. But let's go to one extreme. So we'll go through what's called the PR box. And these names are given in the literature for various reasons. And I won't, it's Popescu and Rohrlich is PR. They came up with, in 1994, a version of this. It was actually done by other people before, but that's not important. We'll just call it what people often call a PR box. But it has the following correlations, or second moments, that the first 3 are plus 1, the last one is minus 1, as shown up here. So that gives S is equal to 4. All right? Pretty simple. Now, it should be obvious that there's no joint probability distribution for this. Because if you think about this, and again, you think about coins, think about 4 random variables here, A0, A1, B0, B1. If the first 3 say they're all positively correlated, again, we can make a little, let's see if we can, let me see, let me try something here. Let's make a little box here. Okay, so let's think about that. So if we have A0 is perfectly correlated with A1, plus 1 correlation. B0, these are perfectly correlated. And again, think of these as coins. And these are perfectly correlated. That's B1. But you're saying that these are anti-correlated, -1. That's clearly can't be the case. Because by the correlations, this is equal to A0 is equal to A1, B0 is equal to B1 in this example. Oh, wait, I made a mistake here. This is not right. I have these slightly off. This goes up here. We can't talk, we're not talking about those. So this is +1. This is +1. But this is -1 over here. But again, the point is, if these two are correlated, and these two are correlated, and these two are correlated, that says that these two have to be correlated. Okay? I think it's, you can convince yourself it's not that hard to show that. Oh, I didn't want all this on there. Okay. There we go. Okay, well, let's go on. This is an extreme case. Now, this cannot be modeled by quantum mechanics. Quantum mechanics does not allow a PR box. But they are of interest in the foundations and quantum information for various other reasons. The other example is just the noise, what's called the noise box. And that's just where all the correlations are 0. So that clearly has S is equal to 0. That's pretty simple. And it's clearly that a joint probability distribution can exist. And this is the other extreme. That's where there is total no correlation whatsoever. And in this case, when we talk about the elementary probabilities, the joint probability distribution, which there's 16 elements, there's 4 random variables, 2 values each. Each one is 1/16. Okay. Now, the next one, I'm going to give a weird name just because it's important, but it saturates this inequality. I'm going to call it the boundary of L box. This means the boundary of what can exist for a joint probability distribution, local set, we call it. But they have the following values. So if the first 3 are a half, and this last one's -1/2, we can see by putting them into here, we get S is equal to 2. And that saturates this CHSH inequality. So this is like the maximum case you can have with a joint probability distribution. You can't have a value greater of S such that you have a joint probability distribution. Okay. So again, it saturates the inequality, and it's important here. We want to go through the joint probability distribution to show that what it looks like. I'm just going to write it down here. You can convince yourself that this is the case. So remember, there's 16 atoms, we call them. If you set these particular ones all to 1/8 and all the other ones to 0, you'll find that you'll be able to get these correlations, and all the means are 0 still. Okay. This is an intermediate between the PR box and the noise box. Notice the way I've been constructing them. The first 3 always have the same value, and the last one has a different value. This means I can make an interpolating formula between these, going from the noise box up to the PR box, as follows. They're called isotropic boxes. That's just a fancy name. Don't worry about it. But we can say, oh, well, the first 3 are X. The last one is -X. So clearly, when X is equal to 0, we have the noise box. X is equal to 1/2, we have our boundary, or saturate the inequality. And when we get 1, we get the PR box. So that's just a way to describe it. And so we can let X vary all the way along. But I want to, again, something that you can convince yourself of, and I would recommend doing it, is to go through and show that the following construction is a joint probability distribution for it. That these set of atoms, there's something missing here, that if we have those first 8, that's the same ones as up here, if those are equal to 1/16, 1 plus 2x, and all the other ones, which can be given just by, are pretty easy to find, but if all the other ones, you see 1/61 minus 2x, you'll find that you'll get this correlations. And again, the means are all 0. But notice what happens when X is greater than 1/2, this becomes negative. So that means that no joint probability distribution exists when X is greater than 1/2. So it's just another way to look at this inequality to understand why it is a good measure to talk about the existence or non-existence of a joint probability distribution. If S is greater than 2 or less than -2, you would say, no joint exists. All right, next thing we need to do is do some quantum mechanics. What does quantum mechanics predict for this value of S? So we need to go back here and look at our experiment and come up with a wave function and see what state we're going to have, etc. So we're going to use our polarization bases again. We're going to use the HV bases as a starting point, and they're going to be aligned for Alice and Bob, but they're allowed to change their angles, recall. So we're going to have Alice's, we're going to look at one pair of settings to do the calculation, then we'll come back and vary them. So we're going to have Alice's setting to be an angle alpha from V, and Bob's to be an angle beta from V. Now the V's align. For Alice and Bob, V and H align. That's important to understand. We'll show that in a minute. Now, the nonlinear crystal that creates the entangled state by spontaneous parametric down conversion, just a fancy way to say that, in type 1 SPDC, the state looks like this. Again, the first ket goes to Alice, the second ket goes to Bob. And clearly it's an entangled state. We examined this in our homework set earlier. Now, the next thing to do is to find the probabilities for the various outcomes. And I want to kind of make a point, I'll make a point here about the rotation angles that counterclockwise is positive. So let's look at the Hilbert spaces and let's look at the first probability. So here's the probabilities. The first probability we want to look at here, but let's look at the Hilbert space structure first. So remember, V and H align for Alice and Bob. Alice rotates through an angle alpha. Bob rotates through an angle beta. This would actually be a negative angle as written because it's going the other way for Bob. But we want to find the probability first. Again, we're going to say V is either -1. Yeah, V is -1, H is +1. So that's, or vice versa, doesn't matter. But we want to see what's the probability that they both come out V. We could call that both plus or -1 if you want, when it's in the state psi. And we know how to do that from our Born probability rule. We take the bra of the probability we're trying to find, VV, and we act on it with our state. And we take the modulus squared. So now we just have to do some work with our kets to get this down. So let's go ahead and fight through this. Now notice here, what we want to do is we want to resolve, because the phi, so use phi plus, is in the VH bases, but Alice is measuring in the V alpha basis, which is rotated slightly. So we want to rank these vectors, for example, Alice's in the blue. We want to get the components that are in the VH, so we can actually do this inner product. So it's not hard to convince yourself that if this vector here, if we just find the components, it's cosine alpha on V here, and it's H sine alpha on H. Actually, looks like it'll be minus. The minus sign is not going to matter. And for Bob, it's going to be similarly. It's going to be cosine beta and sine beta on H. And that's going to act on phi plus. All right, let's crank this through. So now what we do is we multiply this through. First, let's factor out the 1 over square root of 2, so we have a half out front. And we have VVHH. Now we can do this inner product. And it's pretty easy, because we want this first ket to hit this first V. So V on V, that's going to give us 1. So this means that we're going to get this V and that V on this first term, this H acting on that H, acting on that one. And we can quickly do that. That just shows us that this on this gives us cosine alpha, cosine beta. H on H hits this term, we get sine alpha, sine beta, and that's supposed to be square there. There's a square there. And we end up with, using a trig identity, which you might want to look up, is equal to cosine squared alpha minus beta. So that's pretty quick, just some vector resolution. Now, likewise, it's pretty obvious that if we did HH, it's the symmetry here is going to be the same. And if you do HV, you're going to flip the phase a little bit. So I'll leave it to you to verify that the other probabilities are as follows. HH is going to give us cosine squared again. If you mix them HV and VH, you get sine squared alpha minus beta. Okay? So this is what the probabilities are, what quantum mechanics tells us. Okay, we need to go on. So we want to look at how do we do this experimentally. So we want to start tying this to experiment. The way this works is, and I'm not going again to too much detail, what we do is we send out photons and we look at when these two detectors fire at the same time. Now, they can't fire exactly at the same time because that's a null set, so the probability is going to be 0. But you have some kind of what's called a coincidence window, and a coincidence window is a few nanoseconds. But if you say, you can be pretty sure that if these two detectors fire at the same time, they came from the same. They're the same pair. They come from the same pair, I should say, a down-converted pair. And we'll say that the number of counts that occur, we'll call it n alpha beta. Alpha beta being the orientation of the angles. But we do need to change it for whether we're measuring h or v, because h and v are perpendicular. So we want to approximate so again, if we do this, we need a lot of data. So if we do this counting, we're approximating the probabilities. We're not actually directly measuring, we're approximating them. Okay, let's get rid of this figure. I don't think we need it now. But we get this following. There. So again, VV, we get n alpha beta over n total being over all the runs in this particular experiment, where we can look at all these different outcomes. The angles are fixed, alpha and beta. But the next one is HH. We call it alpha perpendicular, beta perpendicular. Remember, what that means is because H is perpendicular to V, that's what this tells us. So really what we would have is we'd have a polarizing beam splitter. One way would be V, the other way would be H. And we're just going to count which way it goes. So on each side, there's 2 photomultiplier tubes. There's 2 on Alice's side, 2 on Bob's side to measure H and V. And again, this is just the ratio of the numbers to the total number. That's how we usually think about it in elementary cases of how we think about the frequentist interpretation of probability. And so we have these cases here. Now what we need to calculate S, we need the second moment, or the correlations. And again, we're going to take the means are all 0. We're going to take that. And in this case, we call it alpha beta for now. A sub alpha, B sub beta, just referencing the angles that they're set at. And remember, the second moment is if they're the same, we have a plus, and then if it's plus 1, minus 1, we get a minus sign. So if they're different, it's minus. We can plug this in. Oh, notice also n total is going to be the sum of these, because in a set experiment, you're going to have these numbers are the total number, so you just add those. So we can write this as this value here, just subtracting off these two, again, so those are negative, and then dividing over the total number there. Also, what we can do is go back to the, from here, go back and insert our predictions from quantum mechanics up here. And that's easy. So we just have to kind of stick them in. And we see that, well, that's a half here, but we have 2 of them, right? So we get cosine squared alpha minus betas, and then minus sine squared alpha minus beta, and that's equal to cosine 2 alpha minus beta. And this is what we want. This is what the quantum mechanical prediction we're after for the correlation. And what we want to do now is look at what does quantum mechanics predict. So we want to look at this form here. So let's consider our 4 random variables. I'm going to kind of draw them out as follows. So let's say A0 is A alpha, A1 is A alpha prime. So 2 different settings of Alice's polarizer, if you will, or a polarizing beam splitter, however you want to think about it. And the same for Bob. But we want to choose particular values here. So I'm going to choose alpha equal to 0, alpha prime equals to 45 degrees. So those are the 2 settings that Alice has had. Bob will have 22.5 and minus 22.5. And we want to look at what do we get for S. So in this case, when we start carrying this out, so we're going to have the following. So it's cosine 2 alpha minus beta prime, 2 alpha prime minus beta, minus cosine 2 alpha prime minus beta prime. And if we stick those in now, notice, let's just do one slowly here. Alpha minus beta, where's alpha? That's 0. This gives us minus 22.5, right? Because 0 minus 22.5, but we multiply by 2, that gives us 45 degrees. And you can go here and notice that the difference between any of these, so alpha beta is 22.5, alpha beta prime, the difference is 22.5 modulo, alpha prime beta, the difference is 22.5. So the first 3 are multiplying by 2, we're going to get 45. The last one, let's look at the last one though, which is alpha prime beta prime. Notice we have 45 minus 22.5, which is 67.5, multiplied by 2 is 135. What that does, because cosine were over 90 degrees, that becomes negative. And we see what that does. So cosine 45 is 1 over square root of 2. We have 3 of them, so we have 3 over the square root of 2. And we're subtracting off this last one, which again is 45 degrees more than 90, so it's just minus 1 over square root of 2. We get 2 square root of 2, which tells us that quantum mechanics predicts that the CHSH inequality will be violated. And it turns out that this value here, 2 square root of 2, is the maximum violation that quantum mechanics allows, which is a kind of an interest in foundations of quantum mechanics, why that particular value. It can be shown, and actually as an exercise, an optional exercise, I would urge you to try it out. It's just some algebra with the operators, because in quantum mechanics we want to represent our observables by operators. You can just, what you do is you square S as an operator, you do the commutation relations, being careful with the commutators involved, and you see you get 8, and you take the square root, you get 2 square root of 2. So the mathematics of quantum mechanics says this is the maximum value. But of fundamental interest in quantum mechanics, in the foundations, is why does Hilbert space work? And why does the mathematics of quantum mechanics describe our world? Why can't we have PR boxes? Because PR boxes do not violate special relativity. So they seem like, oh, that's fine. But there are now principles that limit it, that narrow it down to this, but it's still an open question of what principles define quantum mechanics. Okay. So this is the big punchline here. This is called the Searson bound, if you care. I'll put that out on the course site later. But lastly, let's just look at some data. And again, I'm just pulled some. I'm going to post a paper that's a lab actually report, and it actually shows, it's actually an undergraduate laboratory where you actually do this experiment, because this experiment is becoming so common now that you can do it in it's a little expensive, it's about at least $20,000 to run, but you can actually do this now in undergraduate laboratories, and hopefully maybe one day we'll have it at the OHS. So here again, this is just the data, so it's just kind of showing. You don't have to go through all this. These are the second moments here. These are the values they get, and they get 2.64 plus or minus 0.08, clearly violating S is equal to 2. Okay. Here's a nice plot from another paper. This is actually a recent one, looking at a particular approach to this. We won't get into the details of that, but notice that there are data points well above 2, less than 2 square root of 2, but definitely violating the inequality. And lastly, one that's more relevant here. Here's another one. This one's a little fuzzier. It's showing the angles. Again, it's just some data from various experiments. Here, the S parameter, again, goes up over 2 there. And remember, 2 square root of 2 is 2.824, right? That's 2.828. That's what we're looking at. So that's the red would indicate there. Now, so nowadays, this inequality and others are violated by many orders of standard deviations, I should say, many sigma. So it's quite common to violate Bell inequalities in experiments. There are some loopholes that people are trying to close. You can close some and not others. And maybe we'll come back to talk about it, or I'll put some references up if you want to read further, or shoot me an email if you're interested. I can send you some more materials. There's plenty of material out there. I think that's enough for now.